right. So welcome everyone to the workshop. And as Hugo mentioned, one of the main themes of this workshop is the recent progress in obfuscation. So the purpose of the talk that I'm about to give is to sort of bring everyone up to speed on the constructions of obfuscation, which will be assumed in many of the talks that we'll see later on in the program. And we'll see many interesting talks about obfuscation, covering essentially all angles of the subject. So before we talk about the upcoming talks, let's think for a moment, what is obfuscation? So suppose that you want to keep a secret. And I apologize for those of you who are here at the boot camp. This is sort of a compressed version of my boot camp talk, but I see lots of new faces in the audience, and I hope that you will appreciate this. So suppose you want to keep a secret, and you want to keep the secret from an adversary. But unfortunately for you, the adversary captures your entire brain. Okay? And in fact, it takes your entire brain and reads and tampers with the activity of every neuron in your brain while you are thinking about the secret that you want to keep from the adversary. So this is a very unfortunate scenario, one that thankfully remains science fiction when it applies to humans. But if we think about it, the exact computer science analog of this scenario happens all the time, right? The computer science analog of this is that we have a computer program, which is kind of like this brain, right? The input-output behavior is exactly described by this computer program. And a computer program, in general, in many cases, is completely captured by an adversary, right? The adversary sees exactly what the computer program does. It sees the entire listing of it. And the question we're asking is it possible to keep a secret within a computer program even if the adversary captures the entire program in its entirety, right? And I want to stress that in this situation, we have no trusted hardware, no interaction between parties, right? Just an ordinary program with ordinary inputs and outputs. No encrypted inputs, encrypted outputs, nothing like that, just an ordinary program, okay? And all of this running on, again, an ordinary single computer. Everything about the computer is public. Everything about the initial state of the computer is public. The adversary knows everything about this, right? Before we continue, let's think about how this relates to other concepts in cryptography, especially secure multi-party computation, which will be another major theme that we'll see many talks about in this workshop. This is one of our favorite areas to study. Now usually when we talk about secure multi-party computation, we think of it in terms of many different parties that are talking to each other. But I want to think about it a little bit differently. Let's think about it in terms of our giant brain here. We can think of secure multi-party computation as taking our brain, right, this computation that's taking place with inputs and outputs, and subdividing it into little parts of this brain, right? And in secure multi-party computation, what we ask is even if the adversary can tamper with and read some of these subdivisions, or in the most aggressive case, all but one of these subdivisions, it should still be the case that a secret is kept from the adversary. But again, in secure multi-party computation, and this is really the key difference with obfuscation, there's always at least one honest party, right? One party that is completely blocked and opaque with respect to the adversary. And once we have this idea that there is a part of the computation that's blocked, it leads to the natural solution concept that we've studied for many decades now, which is kind of to spread out the computation using secret sharing or garbling, and in this way make it so that as long as the adversary misses some part of the computation, then he misses all the essential features of it, right? And this is really the main difference, as I mentioned. All these previous concepts required that some part of the computation be completely hidden from the adversary, whereas in obfuscation, no part of the computation is hidden from the adversary. Okay? All right. So that's the vague notion of obfuscation. We want to drill in here and think about specific definitions that we want to achieve. Now, throughout this workshop, we'll actually see many different definitions, and there have been many, many different definitions that have been studied for obfuscation. In particular, Stefano, Omkant, Rachel, and Manoj later in the workshop will all give talks that discuss different kinds of definitions of obfuscation. But today I want to focus just on the most used definition, which is the notion of indistinguishability obfuscation. Okay? So what is an indistinguishability obfuscator? It's a probabilistic polynomial time algorithm subject to a few constraints. First, we just have some basic bookkeeping constraints. Okay? So the first constraint is that when I obfuscate a program, it should preserve the input-output behavior. It shouldn't change the input-output behavior. Okay? And it should at most cause a polynomial slowdown. We're theoreticians, so just a polynomial slowdown is enough for us. Okay? But then when it comes to security, what this definition asks for is the following. If I have two programs, P0 and P1, that are actually functionally equivalent, that is, they have the same input-output behavior and the same size, then no adversary should be able to distinguish between the obfuscation of P0 and the obfuscation of P1. Okay? And I put P0 and P1 here in these parentheses just to emphasize the fact that even if the adversary is told what the two programs were to begin with, even then you shouldn't be able to tell whether the obfuscation came from P0 or from P1. Okay? I also want to stress that on the other hand, the obfuscator itself only sees a single program. It does not know that there is some P0, and that's very important, both in making security meaningful as well as in applying this notion. Okay. Another way to think about this notion of indistinguishability obfuscation is to think of it as a pseudo-canonicalizer. Okay? What I mean by that is that an obfuscation of some program, according to this definition, is indistinguishable from, and therefore reveals no more than, a canonical form of the program, if one exists. Okay? And this is sort of technically what is going on here, right? It's the fact that you can't distinguish between different representations. In other words, you've got sort of a pseudo-canonical form of the program. Okay? Now, this definition was proposed back in, over a decade ago, and there are no impossibility results known for this in the standard model. That's good, but it was an open problem to construct it for a long time. And the first suggestion, the first candidate construction, was given a couple of years ago, and it's turned out to be surprisingly useful after that. There have been really a number of works that have taken this indistinguishability-based definition and leveraged it to actually hide all kinds of interesting secrets within programs. Okay? And it kind of confirms our general sense in cryptography that simulation-based definitions give very strong and easy to understand guarantees, but somehow these indistinguishability-based definitions turn out to be much more versatile than they first seem, and this is definitely the case here as well. All right, so how is it useful? Let me give you just one example, and I'm going to purposefully give you an example that's simple so I can explain it in one slide, but more importantly, it's the type of application that we usually don't think of as being in scope for cryptography. And that's one of the things that's so exciting about obfuscation, is that it takes things that seem to be out of scope for cryptography and brings them into the scope of cryptography. So what's the problem? It's a problem called crippleware. Suppose that I have spent hours and hours and hours, maybe months, years, developing some very powerful piece of software. Okay? And this powerful software makes use of powerful secrets to perform its input-output behavior. Okay? And I want to sell this software to you. But before you buy the software from me, you want to be able to test it out. Right? So what I want to do is give you some sort of crippled demonstration version of this problem, of this software. Right? Now, ideally, what should I do? I should think about what features I can safely reveal to you, redesign from scratch some computer program so that to make sure there are no secrets within it, no secrets that I'm not willing to give out. Right? Spend hours and months potentially making this software and then give it to somebody as a demo software. Right? Now, this doesn't tend to happen. Right? Even in real life, what often happens is that people just take their powerful software and just edit the user interface or some interface aspect of it, right? To just cripple that, but leave everything else the same. And it's a fun thing that hackers do to go in and hack this interface back to its powerful form, right? Or to hack out the secrets that are built into the software, right? Now note that the input-output behavior of these two programs are identical, right? In order to change the input-output behavior, you just need to change the interface, right? So given that, obfuscation gives us a way to solve this problem. It allows us to do this in a secure manner. Why is that? Because, again, these programs are functionally equivalent, I can just obfuscate them using an indistinguishability obfuscator. And by the guarantee of indistinguishability obfuscation, we know that these two programs are indistinguishable from each other, right? And that means that it's safe for us to release this obfuscated version of the program, because we know that if an adversary was somehow able to extract some secret from the obfuscated version, then by indistinguishability, he can also extract that secret from this version. But this version has no secrets to extract, right? Therefore, it's impossible, and therefore, we have security.
So, yeah. You're assuming that in the left software, the hacking doesn't happen by form of an input-output. Like if I provide that ill-formed input to your program, then something like a Stack Overflow happens.
Right. What I'm assuming here is that these two programs before the obfuscation are equivalent. And that's, of course, a critical thing. That's why, there are no free lunches. Obfuscation does not solve all problems. But it does bring into scope things that usually we didn't think of being in scope for cryptography. Yes?
User interface, you mean that there's only certain inputs on which you get an output?
Exactly.
And the program on the right knows what they are.
Yes. So we are assuming that this one, if you built it from scratch, you would only accept those inputs. Right? You wouldn't allow, yeah.
Hardwired the outputs.
Right, exactly. And that's the way this would work. This idea is just one little idea about how we can use indistinguishability obfuscation. And there are many uses of indistinguishability obfuscation. In fact, during the workshop, we're going to see many such cases. Today, Brent and Prabhanjan will talk about it. On Wednesday, Stefano. Thursday, Rachel, Justin, Divya, and Aloni will give us applications of I/O. And on Friday, Omer Paneth will give us some applications of I/O. And there are many applications that are known by now. We could have filled the entire workshop with just applications of indistinguishability obfuscation. There's been so much work in this area. And that's what makes it so exciting, right? That it's so useful. You can do so much with it. Okay? So you're going to see all of these uses. So what I would like to do today is to give you some some sort of grounding in terms of why we should believe that this object exists, right? How do we construct it, and how do we show that it's secure? Okay? So before I do that, just at a very high conceptual level, let me tell you what the main idea is as I see it. Okay? The main idea is something that I'll call structured noise. The idea is that we take the program components that we want to obfuscate and somehow add noise to them. Okay? But this is special noise. This is not just random noise. This is noise subject to this remarkable constraint that if you combine these program components exactly the way you're supposed to, that is, you run the program as specified, then this structured noise will somehow magically cancel out at the last possible moment. At the last minute, the noise will go away, and you will see the output. Okay? On the other hand, if the adversary tries anything else, any other way of combining components, modifying them, doing anything else, then somehow that noise will survive and hide the essence of whatever is going on inside that computation. Okay? That's the idea. That's what we want to implement. Okay? So let me now jump just directly to how this works. And we're going to start with obfuscating matrix branching programs. So let me just tell you what algebraic framework we're going to be working in here. It's the multilinear map framework. And you will hear more about this in the very next talk. So Eric and Mehdi will give a joint presentation that'll go into the details of the latest and greatest multilinear map scheme, the one that seems to resist as many attacks as possible. And they themselves are going to be built using this idea of structured noise. Okay? So I'm not going to go into the details of it, but you'll find out in the very next talk. Okay? But what is the overall structure? What is the idea here? The idea of multilinear maps is to work in a setting where you can do various algebraic manipulations, but there are certain limits to what you can do. Okay? And what are those? Okay, first of all, what's the setting here? First, there will be a certain upper bound k that's established, a certain limit. Okay? And you have levels 1, 2, 3 up to k. And for each such level, there is this object g sub I. And g sub I is just a copy of the integers modulo n for some large random integer n. Okay? And this integer n may have special forms, and we'll get to that later. Okay? Now, what are you allowed to do with these rings gi? Well, you can add. And when you add, you have to stay within a certain ring. Okay, so if you are in GI, you can add another element that's encoded in GI and get another encoding of an element in GI. Okay? You can also multiply across the levels. So you can multiply an encoding in GI and an encoding in GJ and wind up in GI plus J with an encoding again in GI plus J. But this is allowed only if I plus j is at most k. Okay? If it goes beyond that, then you're not allowed to do these kind of multiplications, and that's critical. Okay? And then finally, if you get an encoding at the very top level, at gk, then you can proceed to a zero test. And the zero test will answer actually yes or no. It'll tell you whether or not you have managed to construct an encoding of the zero element. And I want to stress that only the zero test procedure here actually yields unencoded information. Right? All of the other things here are kind of like fully morphic encryption. Right? You take an encryption, you get an encryption. But zero test actually tells you, do you have here an actual encoding of zero or not? Okay? And this is really, really critical to us. Okay? And in this sort of framework, this algebraic framework, we'll eventually state some computational hardness assumptions. Just like we have hardness assumptions over DDH groups or over bilinear maps, we're going to have assumptions in this framework. All right, but not yet. Okay, first I just want to give you some ideas about how to construct obfuscation. All right. So we start with a program that's represented as a matrix branching program. Okay, let me tell you a little bit about what that is. So such a matrix branching program consists of 2k invertible matrices, and it's not a coincidence that we're using the letter k here. And the input length is fixed. In this example here, I have n equals 3. There are just 3 input bits. And they correspond to the colors blue, red, and green. Okay? And these matrices come in pairs. And as you might imagine, we use the bits to select one of these 2 matrices. Okay? So to evaluate such a program on an input x, all we do is take the input, for example, 1, 0, 0 would select these matrices, and just multiply them out. Just multiply them in order. Okay? And that's the output. So the output is just the matrix product of all of these matrices. Okay? And that's our notion of a program. The reason why we care about these programs is because Barrington showed in a celebrated result that all log depth circuits, all NC1 circuits, have polynomial size matrix programs. And something that I won't tell you about is that it turns out that all you need to do is go to NC1. With the current research that we've already done in our community on fully morphic encryption, assuming something like LWE, you can take an obfuscation that works for NC1 circuits and bootstrap all the way up to an arbitrary circuit. Okay? So what we need to do now is figure out how to obfuscate a program that looks like this sort of matrix branching program. Okay? So let's make some progress towards that. The first step is we apply a randomization technique that's actually due to Killian in his celebrated work on building secure computation protocols from oblivious transfer. So what does Killian do? What Killian suggests for us to do, stated in our language here, is we take random square matrices, random invertible matrices, R1 up to RK minus 1, okay? And just pick them at random over Zn. I set R0 and Rk to be the identity matrix just to make things work here, okay? And then what we can do is we can take each of these matrices and left multiply by Ri minus 1 and right multiply by Ri inverse, right? And this is really nice, right? Because this preserves the iterated product, right? Because these R matrices exactly cancel out, right? And the other nice thing is it has this sort of structured noise flavor to it, right? It's only at the very last second, right, at the very last multiplication, that that final R will go away. And we'll make crucial use of that in our construction and proof. Okay? So we've got these M tildes now. Okay? And another really nice thing that we'll make use of is something else that Killian showed. He showed that if you have a specific x, again, think about 1, 0, 0 here, right? Then it is possible to simulate the joint distribution of all of these matrices for that one particular input from just the final product of all these matrices, in other words, the output of this program. Okay? And this may seem a little magical to you if you haven't seen it before, but it's actually extremely simple. And it's sort of an exercise for an undergrad in a linear algebra course. And I won't tell you how to do it, but I encourage you who don't know to try for yourselves, and you can see how to prove it. It's a very simple but very powerful idea. Okay? All right. So we've now taken our matrices and randomized them in this way. Okay? That's sort of step one. Now what are we going to do? We're going to take these matrices and encode them using our multilinear map, right? So that's another nice thing. The way that we've set up our multilinear map, allows for multilinear operations. And sort of the prototypical multilinear operation is iterated matrix product, right? Iterated matrix product is linear in each individual matrix, right? So if we encode every entry of each of these matrices at level 1, once we do the iterated product, we'll wind up with a product at level k, where we can then do zero testing. And it turns out that that's sufficient. These final products will always have a 0 in it that you can test for. Okay? So that's great. It turns out that we're getting now very close, actually, to a plausible obfuscation scheme. But there's one critical attack that remains. There's one intuitively. And that is the input mixing attack. So let me describe that to you. Suppose that I am an adversary, and I'm mostly nice, so I mostly do what I'm supposed to be doing. I start with this matrix over here, and I multiply it with this matrix, multiply it with this matrix exactly the way I'm supposed to. Note now that I am committed to my input, right, 1, 0, 0, and I'm supposed to multiply with this matrix. But nothing is forcing me to do that, right? I could multiply with this matrix instead. And I can start to mix up these matrices in a way that they're not supposed to be mixed up, right? And it turns out that it's a really interesting question, actually, to understand how much information can be leaked in these kinds of with these kinds of attacks. We don't know how to bound it, and there are certainly examples where these kinds of attacks do leak critical information. So this is a real problem that we really need to solve. Okay? This brings us to the question of how to solve it. Here I'm going to be a little bit fuzzy. I'm not going to give you a complete answer, but I'll hint to it a little bit later. So again, remember, what's the problem? The problem is that the adversary could start with this matrix, but then later when he hits another matrix that also corresponds to this input, he can pick the wrong matrix, right? So we have to focus in on the matrices that correspond to a single input, right? And what do we want? We want to force good behavior on the adversary, right? So what does that mean? What that means is that we want it to be the case that if the adversary starts with this matrix, then he has no option. He has to pick this matrix and then pick this matrix. He can't mix and match these things. So we illustrate this with these sort of puzzle pieces that, I want this matrix to somehow be encoded with respect to this puzzle piece. So the only way I can kind of cover my little rectangle is by putting these pieces together in this way. Whereas the puzzle pieces that I have for the other matrices go in the other direction, right? And the only way to put them together is in the other way. Okay? This is obviously not a very technical description of our solution to the problem, but there are actually many ways to solve it. One of the most sort of popular ways now is through this idea of a straddling set. But this is a problem that we do have to solve. Again, I'm sorry, I won't tell you more about it because I just don't have enough time to go into it. But I will come back to this later. The critical point here is that this is a problem that we do have to solve. We do have to think about technical ways to prevent the adversary from mixing up these sort of matrices. Okay? All right. Those are basically the main ideas, okay, that are required to build an obfuscation scheme using multilinear maps and using these matrix branching programs. Okay? We can, if I could have given a slightly different talk where I would have been able to just give you a scheme that we don't know how to break, okay? But we're a little bit further along in our research now. So I'll actually sketch to you a way that we can build a type of indistinguishability obfuscator for which we can actually prove security based on a natural concrete conjecture, okay? And let's think about and now, what do I mean by a natural concrete conjecture? I mean an assumption, right? I promised you anyway from the beginning that I would give you some sort of assumptions over this multilinear framework. So let me talk first about what is the actual assumption. What are we going to assume from which we'll be able to get obfuscation? Okay. So I'll warm up with sort of a special case. Okay. This may seem like a completely trivial case, but let's just think about it. Suppose actually k equals 1. If k equals 1, you have no actual multiplication that you're allowed to do. You can just add things, right? This is sort of a very typical situation for us in crypto. But the one little bit of an issue that will come up more later is that our n will be a composite number. It'll have 2 prime factors, okay? And I'm going to give them names. So we're going to have one special prime factor that I'm going to call C, and one distinguished prime factor that I'm going to call A1. Okay? And when I think about the plain text, when I think about just a number, right, in Zn, I'm going to represent it using the Chinese remainder theorem, right? So I'll look at it, the mod C component and the mod A1 component. Okay? We'll call this the C component and the A1 component, right? Now, we have to give some things to the adversary to state an assumption. So what we're going to do is we're going to give the adversary a level 1 encoding of several things. First, we're going to give a random generator of each prime subgroup except for C. Well, there's only one in this case, just our distinguished prime factor A1. So in other words, I give him the encoding of something that looks like 0, R1. Okay? Remember, this is a multilinear encoding, right? So I'm not actually giving him the number that is 0, R1, I'm giving him an encoding of it, which should intuitively hide the fact that it has this form. Okay? Furthermore, I also give him another element, which I'm going to call H1, which for right now just looks like the opposite. It's 0 in the A1 component, but it has something in the C component. Okay? And now, what I assume is hard in this assumption is that it's hard for the adversary to distinguish between just the encoding of a completely random element versus the encoding of an element that is 0 in the C subgroup, but random in the A1 subgroup. Okay? So again, intuitively what we're doing here is we're assuming that the encoding hides the structure with respect to the primes here, right? This is essentially the subgroup decision assumption without the pairings. Okay, so this is just the idea. For those of you who are familiar with the subgroup decision assumption, this is very similar, but even without any pairing being there. Okay. And indeed, in the next talk, when we see an example, when we see constructions of multilinear maps, they will support these kinds of encodings where there are many prime factors and different things encoded with respect to different prime factors. Okay, so that was our warm-up. Now let's take the next step. The next step is k equals 2, right? So now we have one multiplication that you're allowed to do. And what will change here is that we'll still have our one special prime factor c, but now we're going to have two distinguished prime factors, a1 and a2, right? So we'll add the a2 representation here, okay? I again give random generators for each of the prime subgroups except for c, so those are these two here. And now our h's change. So the h's have something random in the c group, but h1 is missing an a1 component, and h2 is missing an a2 component. Okay, that's the idea of these h's. And now what we assume is that it's hard for the adversary to distinguish between a level 1 encoding of, again, a completely random element or an element that is 0 in the C subgroup. Okay? So let's step back for a moment and just think about this. You know, why does this make sense? And what are we really assuming here? Like, what is the essence of this assumption with regard to the multilinear map? So it's usually good to think about what are the limits, right? You know, what could we wiggle here and then break the assumption? So one thing to note is that I definitely can't give a generator for the C subgroup, right? A generator for the C subgroup would look like this, R00, 0. Then what I could do is just multiply the T element with GC and then 0 test, right? In this case, I would get a non-zero outcome, but in this case, I would get a 0 outcome, right? So this would be one way of breaking. So it's very important that I'm not giving that out, right? That's one thing to think about. The other thing is that we're very much relying on the fact that there is a bound of 2, right? That the max level here is 2. If the max level was 3, then again the assumption would be false, right? Because then what I could do is multiply t by both h1 and h2, which would eliminate the a1 and the a2 component, and therefore again yield 0 in this case and non-zero in this case, right? So, and indeed that's why we're going to eventually call this the elimination assumption, because we have these elimination elements which allow you to eliminate, but we set our max multilinearity at just the right level so that you shouldn't be able to test. Okay? And I want to stress that this is also something that we've seen many times in cryptography. So, for example, the bilinear assumptions that we typically use, if we could have a trilinear version of that map, most of them would break, right? The DLIN and the BDDH assumption, all these things would break if we just had if we could just go from 2 to 3, right? So here too, we want to very critically use the fact that we're putting a specific bound of k here. Okay. All right, and then the actual assumption that we're going to make is just the k analog of this. Okay, with one little additional thing. So now we go to k, a general k. It'll be the k multilinear subgroup elimination assumption, and we'll have again one special prime factor c, k distinguished prime factors now, a1 through ak. And then there'll be some polynomial many other primes. I'm not going to really talk about them. They're not going to play really any role in the assumption, but we need them for some technical reasons. Again, we have our CRT representation. We always start with C and then the distinguished primes. Okay. The adversary gets generators of every prime subgroup except for C. And then these HIs are these eliminators, right? So again, they're random everywhere except exactly at the AI component. So HI is 0 in the AI component, right? And again, it's hard for the adversary to distinguish between something that's completely random in all the distinguished and special primes, or one that is random in the distinguished primes but not the special prime. Okay? And this is the assumption that we want to make. And indeed, as far as we know, there are no attacks on this assumption using the latest and greatest multilinear maps that we're going to hear about after the break. So, all right, this is our assumption, and now we want to leverage this assumption to actually build indistinguishability obfuscation. Before I do that, I want to stress right now, look at this assumption, right? There are no matrices here, there are no programs here. So, we'll need to do some work, right? We need to somehow take an assumption that doesn't have anything obfuscation-like in it, and we want to somehow reduce it, which is what we always do as cryptographers, right? All right, good. So how are we going to do that? What's the plan? What's the game plan here? How are we going to argue security for obfuscation? So we need to prove indistinguishability, right? We need to start with an obfuscation of C0 and move eventually to the obfuscation of C1. These are equivalent programs, meaning they have identical input-output behavior. But still, how are we going to do this? How are we going to start with these encoded matrices and somehow wind up with these completely different encoded matrices, right? C0 and C1 in matrix form, every single matrix could be different, right? So what's the idea here? Well, we're going to give a hybrid argument, what we always do in crypto, right? And since we're giving a hybrid argument, inevitably, we're going to have to somehow, slowly, switch out some part of the C0 computation and switch in some part of the C1 computation, right? That's just inevitable. We have to do that since we're starting with C0 and we're ending with C1, okay? The question is, how do we do it? So the key idea here is to use the one thing that we have in our hand, which is Killian simulation, right? We've already seen that when you're restricted to the matrices that are needed just for a single input, in that case, information theoretically, the matrices that correspond to C0 are identically distributed to the matrices that correspond to C1, right? So that allows us to information theoretically move between C0 and C1, but only for a single input. So then the main work that we have to do here is to somehow go over every single input and transfer it from C0 and move it to C1, okay? So the way we'll do that is by actually having 2 to the n hybrids in our hybrid argument, where again n is the input size. This may seem a little bit worrisome to see a 2 to the n in the high number of hybrids, but again, this is okay by complexity leveraging, something that we've seen many, many times. So if we assume something is sub-exponentially hard, then by choosing the security parameter in such a way that the security parameter to this epsilon is greater than n, then we can have enough hardness so that we can actually go through 2 to the n hybrid arguments and still have sub-exponential hardness left over in the end. So in fact, we'll assume sub-exponentially secure multilinear subgroup decision elimination assumption, and we'll end up with sub-exponentially secure indistinguishability obfuscation. Okay? All right. So let's zoom in a little bit more on this strategy that we're building here. The idea is, again, to isolate each input, right, so that we can apply Killian. So how will we do that? We'll do that by having polynomially many parallel obfuscations, okay, where each of these parallel obfuscations is responsible for a different bucket of inputs. Okay? And how will this work? Well, we'll have 2 types of hybrid steps. In hybrid type 1, all we're doing is reallocating inputs between 2 obfuscations of C0. So I have one bucket for C0, another bucket for the same program C0, and I'm just moving some inputs from here into this bucket. Okay? This is actually the place where we'll use our assumption. Okay? The second type of hybrid arises when we have managed to get just a single input isolated in this bucket, right? Then this parallel obfuscation will only have those matrices, right, that correspond to a single input, and we'll be able to apply Killian and switch over to C1, information theoretically. Okay? And we'll keep doing this until eventually we've moved everything over into the C1 bucket. Okay? All right. Excuse me. So you can see here that this is basically information theoretic, right? So all of the work is happening in hybrid type 1, right? Let's think about a different way of thinking about hybrid type 1. What we're basically asking is the following. Suppose that I had some code that looked like this sort of strange looking code. What does it do? It checks if the input is less than or equal to 37, If so, it runs C0 of x. Then it checks if the input is either 38 or 39, and it runs C0 of x. This is the same thing, but just does it in two different places, right? Otherwise, it runs C1 of x. Okay? Hybrid type 1 is basically like taking this code and just modifying this from 37 to 38. I'm just reallocating the input 38 from this branch to this branch, where both branches do identical stuff, right? The code is actually identical. This seems like such a minor change, right? And yet, sort of the key lesson of this is that the ability to make just this very minor change is actually sufficient. If we can do this, we can go all the way to obfuscating arbitrary programs, matrix branching programs, that are equivalent to each other. Okay. All right. So let me zoom in a little bit more on what's going on here. So suppose we start with some obfuscation, normal obfuscation like the one that we saw. In the beginning, we'll just create sort of a parallel copy of this obfuscation. And now sort of the key step will be to sort of bifurcate the inputs. So what I mean by that is we'll zero out the 1 matrix here and the 0 matrix here, right? And if we zeroed out this matrix and zeroed out this matrix, then we've split up the inputs, right? 1/2 of the inputs go here, 1/2 of the inputs are covered by this, right? And this is, again, the key part where we're going to make use of the assumption. Then we can keep doing this, right? We can pick another place, keep doing it. And eventually, if we keep doing this, we'll eventually isolate a single input, right? And as I said before, now we can apply Killian. We need to be sure, though, that this parallel obfuscation is using R matrices that are completely independent of all the other R matrices in order to be able to apply Killian, but that's what we'll do. Okay? And we switch over to C1. And now we finally got our first input that's actually handled by C1, and all the rest are handled by C0, right? But we've gotten started, right? And now we can isolate the next input, move that to C1. Then we could merge the two C1s together in the same way that we bifurcated the C0s here, right? And in this way, eventually, we'll wind up with everything just in the hand of C1, and that is an obfuscation of C1, right? That'll complete the hybrid. So, again, the key, yes? Yeah. I mean actually replace with the all zeros matrix, right? So this matrix, in other words, if I try to evaluate this, if I ever have an input that starts with 0, then I'll end up with just a matrix of all zeros in this component, in this parallel obfuscation. So I literally mean zeroing out that computation. Yes?
The new obfuscated program is all of these things together.
All of these things together, yeah. And I haven't told you exactly how to do that, but I'll tell you that in just a minute.
Do C0 and C1 have the same structure as a branching program?
Yes. So what we're assuming here is that C0 and C1 are both branching programs, oblivious. They all have exactly the same size and all of that.
But also like the same input bits in each.
Yes, exactly. They all go, blue, red, green for the blue input bit, the red input bit, and the green input bit. It's easy to do that. This is just an obliviousness thing. You can just pad with identity matrices, so it's not an assumption. But it is critical. We do need that. All right. So, very good. So this will eventually complete this. Yes?
So, can you replace the hybrid with nested hybrids?
I'm not sure what you mean. Yeah.
So, the hybrid argument, can you replace it with nested hybrids? So it's a new technique. So you can go from 2 raised to n to 2 to the log n. It's a new technique. I don't know whether you're aware of that.
Oh, okay. You're saying, is there a way that we could? I don't see how to make that work. But I'd be happy to talk with you offline about it. Yeah. So, all right. Very good. So again, the key thing, right, to make this work is exactly the zeroing out of a matrix, right? What we need to do is, if I have these two parallel obfuscations, I need to be able to sort of look at this one matrix in the eye and just zero them out, right? And I needed that to be indistinguishable to the adversary, right? So that's like the elementary operation that I need to be able to do. And that's where I'm going to be using my assumption, right? So let's think about that. What could we use in our assumption to zero out something? Actually, it's right here, right? That's exactly the way we've made the assumption. It allows us to go in the special prime factor from something random to something that is 0, right? So this means that what we'll do is we'll think of these parallel obfuscations as happening with respect to different primes, right? A1, C, and so on and so forth. And I'll assign C to this one, and let's say A1 to this one, okay? And now if I use T, right, that I get from the assumption, to create these two encodings, I'm done, right? Because if T came from the first distribution, then both of these matrices will exist. But if it came from the second distribution, then this would be zeroed out, right? So that is the essential step that we need to do here, okay? Now I also need to make all of these other matrices. That's the part that I won't go into too much depth on. But the essential idea here is that I need to use the HIs for I not equal to 1 to make the rest of these. Now why? It's because I need that in both cases, right? No matter what T is, I need all the other matrices to exist. So they better always be non-zero with respect to C and with respect to A1. And that is the case for all of these HIs for I not equal to 1. That's the way they were made, right? Okay. Now, there's still that issue of the input mixing attack, right? Again, I'm not going to give you the details, but the essence of it are these missing points in these HIs, right? These HIs were random everywhere except at one little point where there was 0. That is the idea. That is the key feature we use to be able to enforce input consistency. So the fact that there's a missing thing there is actually used exactly to force good behavior on the part of the yes. Actually, no. The number of primes is the number of parallel obfuscations, right? So that actually has to do with, it's going to be something that's a polynomial in n. In fact, it'll be a linear in n. So that has to do with how many cases do I need to subdivide before I've isolated an input, so that I can do this traversal, right? I need to traverse my way through this tree to go from all C0 to all C1.
What's the number of primes you make in general? How is it related to the time of the branching program?
Right. It will not be related to the length of the branching program itself. It'll be related only to the input size. Right. The input size is fixed, but whatever that is, it'll be linear in that.
You have a read once branching program, whatever there will be once, then you just need a constant number of primes.
No. Again, it'll be the number of input bits, right? So if the input length is n, then I'll need something like 2n prime, something like that, 3n. Yeah.
Just to follow up on that, if we
Yeah.
did have a read once branching program, does it help in any way?
It turns out that read-once branching programs are really uninteresting to obfuscate.
Second
But
problem will get solved. You don't have the
yes, exactly. These kind of things get sort of solved for free in situations like that.
assumptions or including the assumptions.
Again, it trivializes in that case because there's sort of nothing to be done. But for obfuscating them, that depends on exactly how we define the notion of a matrix branching program. I skipped that part here. If you use the Barrington definition, then there's really nothing that can be done. If you use a different definition, then actually we need to do some additional randomization to make this work, which I haven't talked about. In that case, it does become non-trivial. Yes?
How do you evaluate this parallel obfuscation? Don't you have to sort of know which column you're in?
Right, no, so that's the nice thing. The point is that each of these parallel obfuscations is just in different primes, right? So when I evaluate one obfuscation, I'm actually automatically in parallel evaluating all of the obfuscations. And if all of them are 0, then I'll zero test, right? And if any one of them is non-zero, then it'll look like it's non-zero, right? So when I zero out something, I'm just taking it out of consideration, right? It's not going to affect the outcome. Okay. All right. So that's the rough idea of how this works and how we're able to reduce obfuscation to a concrete natural assumption that that doesn't have obfuscation within it. And I just want to stress that point again. The reduction that we're describing here, the programs are all fixed, right? The reduction knows every single matrix here that's involved. We don't need to hide that from the reduction at all. If you think about it in that like if-then thing that I showed you, the two cases, right, that are known to the reduction, P0 and P1, they tell you what the programs are. It's only the inputs that get moved around, right? So that's really critical, and it allows the reduction just to directly build all these matrices. It doesn't need to take them from the assumption or anything like that. He can just build them himself. Okay. All right. So that's sort of my yes.
In the end, how many sets of matrices does the program going to have? Is it going to be n of them?
So you mean like how many parallel ones? Yeah, that's what Hotek was asking. It's going to be something like something linear in n, something like 2, 3n. Yeah.
So you're saying each of those parallel universe you cannot actually evaluate it. I mean, you evaluate it, but you get something encoded, and even though it has 0, you cannot test or something.
No. So what you're testing for is that all of the parallel evaluations evaluate to 0, right? If they all evaluate to 0, then when you do all these iterated matrix products, you'll get a matrix which will have one element that'll be 0 everywhere, right? And then you can 0 test for it, and that's fine. And remember, it's critical that C0 and C1 are functionally equivalent, right? That means that their output is always going to be identical no matter what on any input. And that's very important here.
Using the assumption you zero out this matrix, obviously if you could evaluate, you see you put the first input to be 1, x0, x1 to be 1.
No, hold on.
You get 0 and non-zero, so you obviously...
No, hold on. Remember, the input selects all of the parallel obfuscations at once, right? So if you selected this matrix, you're automatically selecting this matrix, all of that, right?
If I know that this is the assumption that you're going to use to zero out the right matrix, I'll select x1 equals to 1, and then obviously I will see that this is 0, this is non-zero, so, I mean...
No, because it'll be blinded by this guy, right? Here M1 exists. So if you tried to just take this part, you've also taken this part. And when you evaluate...
It's just one program, some could not like...
Yes, it's not n programs, it's all one program that are just combined using CRT, using Chinese remainder theorem. Yes, that's what I meant by here. We're using the Chinese remainder theorem to, inextricably, link all these things together. Yeah.
So just to make sure, so
Yes.
like what I was asking, so at the bottom, you're outputting the OR of all these programs, and the ones that you've zeroed out,
It's almost like an OR. It's kind of it favors 0 versus non-zero. But what is the guarantee that we need? We need that if all of the programs agree on the output, then the output is correct. If they don't agree, then we don't care, because that'll never arise in our hybrids, right? Our hybrids only ever apply to functionally equivalent programs. Yeah, they all agree on one. Yes, they all agree on one output, or they're 0. In which case, they're just out of consideration, right? Their output does not affect whether the final output is going to be 0 or non-zero. Does that answer your question? Kind of. Okay.
so you have these hybrids, and then you want to go to C1, right? So at the last hybrid within C0, you want it to be a single input, single output, right? So
Yes.
going back to level,
Yes.
all of this is you explaining to me as the hybrid within one program.
Mm-hmm.
And so at the last hybrid
Yes.
within the one program, what do you have?
Yeah, so the last hybrid you'll have will look like this. So you're exactly right that we'll have, with respect to C1, we'll have a bunch of programs, right, that cover kind of everything, except for, with respect to C0, we'll just have the last input. Maybe it'll look like this, just for simplicity. Right? All these are 0. Right? So remember that these are functionally equivalent. So if I evaluate it at the, let's say, 0 to the n input, right, then I will get the same output here as I will get here, right? So if the final output is 0, then it'll be 0 in both places. And if it's non-zero, then it'll be non-zero in both places. On the other hand, if I evaluate it on some other input, let's say 1 to the n, then this part just doesn't contribute. It'll just be whatever C1 does. That's the idea. All right. Yes.
Is it correct to think about it as evaluating over the product? Like this is what you mean by CRT representation?
Exactly. Yeah. We're evaluating, because each individual encoding has components from all the different parallel obfuscations. When you finally evaluate it, you end up with something that has a CRT representation of the output in every, with respect to each prime. Right? And they all have to be 0 for it to be 0 testing to 0. Yes?
So the 0 test at the end checks if it's 0 in all the...
In all of the places, exactly.
If it's not even 0 in one, it's like the answer is not 0.
Exactly. If it's not 0 in even one, then the answer is interpreted as non-zero.
Okay, so that is somewhat like OR.
It is like OR, but it's just slightly different because one is being used to select an input and one is an actual OR, right? Yeah. Yes.
It seems like all of these n primes. You said 2 n or 3 n primes.
I just need a little bit of room because I need to be able to do this dance of moving things around. 2n is probably overkill. Maybe we need n plus 3 or something like that. But yeah, we just need to be able to have enough room to do this dance. Yes.
Just understand the assumption. The product of all the primes is known. Also, so the adversary. Yes.
The composite number n. It could be known or it could not be known. It's actually not needed here. It's not needed here. Yeah.
So that will go into the actual construction of the multilinear map, whether it's known or not.
Exactly. Yeah. We don't need it to be known.
So there's no factoring assumption here, in other words.
There's no factoring assumption here. Yeah. Okay. All right. So that's that. Yes.
If the prime numbers are known, is it obviously insecure or not? So
If the individual primes are known, yeah, then it's hopeless.
So the assumption seems to be that we could always zero out the special prime, right? So we're zeroing out among all of, within this single hybrid, we're zeroing, right?
Right. The critical point here is that you actually cannot. Well, yeah. Okay. Sorry. Do you see what's going on here? So we cannot. You should not be able to zero out all of these, but not the special one. That would allow you to distinguish, which is exactly what we have. Okay. Yes.
So in your picture, when you're zeroing out, say, the first bit, or the matrix corresponding to the first bit, are you actually zeroing out all of those matrices corresponding to the first bit at the same time?
I don't need to, but I was hiding that. We will actually have different hybrids. We will zero them out one by one.
But then, doesn't K have to be proportional to the length of the program at that point, as opposed to the length of the input?
K is always proportional to the length of the program. K is the level of multilinearity. That was always the case. Sorry, the number of primes is different. That's n. The number of primes is with respect to the length of the input. Okay. Okay, yes.
The way you describe it, it seems like you're looking at constant of both primes, right? And one is the real computation, the other one is the functional computation, and then you switch from 0 to 0.
I don't know how to do that. Let me just. I'll just draw another quick picture to illustrate what we need. So think of it as a binary tree. And it's kind of like a pebbling problem. So the basic step allows me to take a pebble that I have here and cross it out and get 2 pebbles here, right? And what I need to do is I need to reach the leaf, right? So when I reach these leaves, I have all these pebbles, which is like n pebbles, right? And then I can switch this from C0 to C1. I can switch this from C0 to C1. And then I can bring them back up, right? I can combine the 2 pebbles and get a C1 pebble here. Right? And then I can do this. You see what I'm saying? So for that reason, I seem to need n primes. The root node, yeah, so the root node corresponds to all inputs, all 2 to the n inputs. Okay. All right, we will actually have a discussion phase after the next talk, so maybe I'll take the rest of the questions then. I just want to talk briefly, stealing a few minutes of your break, I'm sorry about that, about where we are, where we, as opposed to where we want to be with respect to obfuscation. There's a huge amount of work to be done here, right? So first of all, we have this assumption over a candidate map. So what is that candidate map? You'll find out in the next lecture. So Eric and Mehdi will talk to us about that. And why does this assumption seem to be secure despite recent attacks? There are ways that we can defend against them. Okay. Once we've done this, we can bootstrap. I already mentioned that. And then this afternoon, Brent will tell us about how to bootstrap to Turing machines. And then there's some breaking news. Justin will tell us how to go to RAM programs in the breaking news session. And we can even achieve constant multiplicative size overhead in the obfuscation. So the size of the obfuscation can in fact just be a factor of 2 bigger than the original unobfuscated program, plus some significant additive factors, but let's put those aside. And Pramanjan will tell us about that this afternoon. But again, these are new assumptions, right, and new M maps, which is unexplored space. So what can we do about that? So there are a few ways forward. Right now, with regard to multilinear maps, we're in this sort of attack-defend cycle, right? We want to come up with new math, we want to then attack it, and then build it back up, which probably doesn't leave all of us very satisfied, but it's been a very successful way of doing crypto for the last several decades in the sense of block ciphers with the AES competition, even bilinear assumptions over specific elliptic curve families. Specific elliptic curve families were attacked over time and all that. That's where we are right now. It'd be great if we could get out of that. It'd be wonderful if we could, for example, reduce the multilinear subgroup elimination assumption to some nicer assumption by building a new candidate M-map scheme with the goal of targeting this particular assumption, right? That would be great. I don't know how to do that. And of course, we could also explore entirely new ways to build I/O, right, which could potentially give us other assumptions that we could use. And there's some really exciting partial progress towards this. So a new paper by Ananth and Jain and Bitansky and Vakuntanathan, but 2 papers, I should say. So you'll hear about this on Wednesday afternoon. Abhishek will present it. And what they do is they show how to build indistinguishability obfuscation from another primitive called compact functional encryption. Unfortunately, currently we only know how to build this primitive using I/O. So far we haven't made progress, but there's hope, right? Potentially this other primitive, compact functional encryption, maybe we could build it without using I/O, which would give us another route to I/O, which would be great, right?
Aren't they equivalent?
Yeah.
Or,
What's that?
Isn't the implication easy? So essentially, compact functional encryption is just another name for I/O? I don't know.
No. They're different in flavor, and you'll hear about this on Wednesday in more detail. But they're very different. They're very different primitives. This is a non-trivial proof to show how to go from compact FE to I/O. The other direction is also non-trivial to go from I/O to compact FE. So, and in fact, there are many FE schemes that don't have the compactness properties, even using I/O. So there's really a lot to explore here. Okay, and then finally, I want to leave you all with something a little bit more adventurous, which some of you who may have already seen. So, cryptography is all about hardness, right? Not exactly. We also have information threaded cryptography, which I know and I love. We all know and love it. But let's put that aside for the moment. But essentially, cryptography is about leveraging hardness, right? And if we think about the evolution of our field, it's remarkable how it's proceeded, right? We started with these sort of basic assumptions about RSA, DDH, and factoring, and we built these beautiful objects, right? This public key encryption, multi-party computation, zero knowledge, signatures. In fact, it's so really beautiful that if this is all there was to crypto, we should all be happy, right? It's so beautiful, right? We could spend our entire lives just watering this one little part of our hardness landscape, right? But that's not what happened, right? In the early 2000s, these new sources of hardness came, these bilinear assumptions. And out of those grew identity-based encryption, attribute-based encryption, short signatures, beautiful, wonderful stuff, right? And then there was Gentry's ideal coset problem in LWE, right? Another new source of hardness, out of which we got this amazing object of fully homomorphic encryption, and many other things, right? And now finally we have this new source of hardness of multilinear map candidates, and we have this amazing stuff coming out of it: obfuscation, crippleware, and lots of stuff that you'll hear more about later in the workshop, right? So what about all this other space, right? We've only really kind of begun to explore the sources of hardness that are actually present out there, I think. And I think we should all really think about that, right? That sort of the evolution of our field has been with new sources of hardness, and we should think about how to leverage that. So just to conclude, obfuscation, I think I'm really excited about it, as you probably guessed. But it's still in its infancy, right? We really need a huge amount of work here. And I think that we have to be willing to take risks. I think that we should be, that's another sort of lesson from the previous slide, is that taking risks have really paid off, right, for our field, and we should continue to do so. I didn't talk about it much, but efficiency is a major, major bottleneck. This is the anti-theme, anti-efficiency theme in this workshop. So we have polynomial time, we even have constant size overhead, but the computational overhead is huge. It's polynomial, but the constants, easily exceed 2 to the 100, small numbers like 2 to the 100. That's probably something we should address. Finally, you'll learn a lot more throughout the rest of the workshop. So thank you.